Today's topic is potential energy, voltage, and electric fields. Three ideas that are often very confusing. Their equations are very similar, and they're very much like the force equation. So we're going to try to differentiate between the three of them and get their equations straight. Okay, one of the things you need to remember is your potential energy is measured in joules. And remember, energy, work causes a change in energy. So our work is our force times our distance. So if I have these two positive charges and I want to move them closer to each other, I've actually got to push the little blue positive charge towards the negative, because the natural tendency is that these guys would like to repel each other. So I've got to push it towards it. And so when I do work on it, because I've applied a force over a distance, when I do work on it, I give it potential energy. So it's got a gain of potential energy. If instead the charge was negative, then if I bring it towards the negative charge, it wants to be by the positive charge. It likes that. And so I don't have to do work to do it. The charge itself is doing the work to pull it. And so as it gets closer and closer and closer, the negative charge is going to lose potential energy. This is kind of like if we take a rock or the book and let go of it. So if I'm holding it here and then I let go of it, it's going to want to naturally move towards it. So it has potential energy out here. It's going to lose potential energy. That potential energy is going to get turned into kinetic energy as it moves closer towards it. So remember, we have our force equation, K, Q1, Q2 over R squared. So that's our force. And then we're going to multiply by our distance. Okay? And the distance is just like the radius here, and that's going to cancel out one of those R's. So our potential energy, or our change in potential energy equation, is going to be K, Q1, Q2. So it does depend on both charges over just the distance between them. So if we're going to find a change, we would do this twice, or this would be, the R would be the distance it moved. So do you see how these two equations are very similar to each other and are very easy to get confused? Now our potential energy is measured in joules. And so that's one way we find potential energy. So you want to put this equation on your equation sheet. Alright, so here's where it gets confusing. So your book is going to talk about electrical potential. Sometimes the problems will ask about electrical potential. That is your voltage. Okay, so don't get it mixed up with electrical potential energy. You'll see on the pretest, whenever I talked about energy, I wrote out the word energy so that we didn't get energy and electric field confused. And whenever we were talking about electrical potential, I just wrote voltage. I didn't call it electrical potential. So I'm trying to get those terms straight. So electrical potential is also your voltage. So when we have a 1.5 volt battery, okay, so if we have a battery that's 1.5 volts, that means that there's the potential, there's a push for the electrons to go from one end to the other of 1.5 volts. So your voltage is basically your joules per coulomb. Okay, so volts and joules per coulomb are the same thing, and we're going to use this idea to also derive our equation, because joules, remember from the previous slide, we had K, Q1, Q2 over R for our voltage, for our energy. Okay, now we're going to divide that by a charge, Q. So it's kind of like electrical field, which we're going to get to in a minute. So one of the Q's are canceled. So your voltage is your K, Q over R. So it depends on how far from that charge you are. Okay, so remember, everything in electricity is based on what happens to a positive charge. So if I'm really close, I'm going to be dividing by a small number. I have a lot of electrical potential energy, so I have a lot of energy because I'm close, but you can look here, I'm going to be dividing by a smaller number. So if I'm close, I have high voltage. If I'm far away, I have low voltage. Okay? Because I have more potential energy here when I'm closer and less potential energy over here when I'm further away. And so a positive charge is always going to move from an area of a high voltage to an area of low voltage. This is what a positive charge does. A positive charge is going to go from high to low. So an electron is going to go the opposite way. Okay, an electron wants to go towards this positive charge. So an electron is going to go from an area of low voltage to an area of high voltage. Now, you can have negative voltages. A negative voltage is a voltage produced by a negative charge. So this charge here that's producing the voltage, just like when we do electric field, this charge here that's producing the voltage, it's your distance from here. If this was negative, then you would have a negative voltage. Okay, and so a lot of times what we're looking for is the change in voltage. How much voltage changes as I move from here to further away. We're going to talk real quick about equipotential lines. So if I have this positive charge, the voltage everywhere along this circle, and everywhere along this circle, and everywhere along this circle, assume they're perfect circles, sorry. So here we have high voltage because we're close to the positive charge. Over here we have low voltage, but everywhere along the circle has the same voltage. So if I wanted to take a little charge and I moved it along an equipotential line, everywhere along here has the same voltage. So this doesn't require any work. I can go near because the energy here is the same the whole distance around, so that doesn't require any energy. But if this is a positive charge and I want to move it to an area of high voltage, I need to do work to do that. And so I would find the difference between these voltage lines, okay, and my charge, and that would help me find my work, because you know your volts are your joules per coulomb. You can also get your joules by multiplying your volts times your coulombs. So your energy is equal to your volts times your charge. But that's just a rearrangement of this idea here. So that's just a rearrangement of the equation, but it's another way to get how much energy or how much work. So this is your change in energy, is your change in volts divided by the, or multiplied by the charge. If I'm going from high to low, then I'm going to lose potential energy. I'm going to gain kinetic energy, but I'm going to lose potential energy. So that's what equipotential lines are. And remember we talked about electric field? And the electric field lines always went away from the positive. Okay, so if you look at your electric field lines, these are the electric field lines, the pink ones are electric field. You'll notice that they are always perpendicular to your equipotential lines, because everywhere along the blue circles is the same voltage. Everything, the electric field lines will tell you which direction a positive charge is going to go. So your electric field is your force per charge, or your newtons per coulomb. Your volts is your energy, your potential energy per charge. It's your joules per coulomb. We also know that your energy is equal to your change in voltage times the charge. So rearranging this top equation, we get that the force is equal to the charge times the electric field. And we know our energy is also our force times our distance. So we can take this and stick it in here, and then we get our change in voltage times our charge is equal to Q times E times D, which is also our energy. Okay, so another way to get your potential energy is QED, which might sound familiar from geometry. That's how you ended proofs. So that's another, so it kind of they're all interrelated, and there's different ways to think of the different things. Another thing that we can use is the voltage. Since our voltage is our joules divided by our coulombs, and our joules are QED. QED divided by Q, our Q's are going to cancel, so our voltage is also the electric field times the distance you moved it through. So a whole bunch of different ways to look at things. Okay? And which you used kind of depends on what you're given. So all of these equations are related to each other. They're derived from each other. So don't freak out that you've got like 20,000 equations. They are all derived from each other. And they're all derived from these basic relationships that the electric field is our newtons per coulomb, our volts are our joules per coulomb, and our energy is our force times our distance. So they're all derived from that same basic idea. So that's the big picture, and then we'll do some sample problems in class tomorrow. We'll see you later. Bye-bye.